Hello everyone, my name's Jacob.
My name is Keigo.
And my name is Jorden.
And this is our design for a low-power 3D printed myoelectric prosthetic hand.
The starting point of our project is the movement of the human hand. While many prosthetic hands represent simple and minimal grasping motions, we thought that grasping motions in daily life might be somewhat different than what many prosthetic hands replicate. Of course, it depends on the situation, but human grasping motion is fluid, not mechanical. The grasping motion starts with the little finger and ends with the hold of the index finger and the thumb. We believe that this kind of grasping motion is effective in grasping objects in daily life. Therefore, our project goal is to develop a 3D printed myoelectric prosthetic with a more natural directional curve of the fingers. I'm gonna talk about later the details.
This project can be thought of in terms of 4 high-level functional blocks. The first of these blocks is obtaining the myoelectric biosignal. The second block would be to filter that signal and amplify it so it can be used by electronics. The third would be to feed that now processed signal into a microcontroller, and then that microcontroller will use that signal to actuate the servos that will control a prosthetic.
To develop the hand, I used SolidWorks to develop the prosthetic hand, Ultimaker Killer for output, and the Clarity in the 5 Pro for 3D printing. The prosthetic hand is divided into several parts, each of which was designed based on the dimensions of an actual hand part. Okay, first, the prosthetic hands we envision will mimic the anatomical grasping motion of a person for use in daily life. In the human grasping motion, each finger does not move simultaneously, but each finger and the mother and the little finger balls move correspondingly. And imitating these movements is beneficial to the prosthetic hand user in 2 ways. The first is that it is easier to reflect the prosthetic hand's user's desired movements. Before and after the amputation, the operation of the prosthetic hand depends on its complexity and reproducibility. If we can mimic human movements, we expect that the user will be able to get used to the prosthetic hand more easily. The second is daily use. Many prosthetic hands that have been developed flex horizontally against the MP joint. However, when performing daily grasping motion, each finger does not flex in the same line, right? And the pinky and the ring fingers curl inward slightly. This is where we focus our attention, as imitation of the movement leads to the reproduction of such movements that are really necessary in daily life. The grasping motion is mainly performed by the pinky ball and the little finger. Here. While the index finger acts as a support to prevent the other fingers and the object from falling when performing the grasping motion, like that. So in summary, our project is to create a myoelectric prosthetic hand that mimics the movements of each finger, starting with the little finger. So I was in charge of the mechanical design. The software we used was SolidWorks I took measurements of the hand, remodeled the rough shape of each part, and proceeded to 3D printing. In order to integrate the movement of the motor, each joint has holes, like here, holes on the dorsal and the palmar sides of the hand for cables or wires to pass through. Also, an elastic cord is threaded through the dorsal side of the hand, and its elasticity allows each finger to return to its original position after flexion. So, for the 3D printing, we used Ultimaker Cooler for data output and the Clarity in the 5 Pro for printing. The material used was Eco-PLA, but different materials were used for the distal phalanges and the palm part due to the melting temperature for printing. The 3D printing processes took about 3 days. During the process, the nozzle clogged and the adjustments were made. The rest of the process went without a hitch. After the initial printing, I realized that the middle finger needed more clearance to allow for a smooth bending of the joint, so I remodeled it. Thank you.
You can think of your body as a various network of interconnected circuits with various voltages, currents, and resistances flowing within your body as well as covering your body. So one of the main things that we looked at when designing the prosthetic was the resistance of the skin as well as the frequency of EMG signals, specifically the usable dominant range between 50 and 150 hertz. With that, we used a voltage follower followed by an op-amp circuit and calculated our resistances and capacitances in order to build an effective circuit that would filter out those EMG signals. So, shown in the image, we ran the simulation in LT-Spice to show our expected outcome of about 1.2 to 1.5, definitely below 2 volts. Shown here is the circuit that was built out. We have all of our resistors, capacitors, wires, connections, everything in place. At the top right of the left image, you can see the servo motor. We used an Arduino and a breadboard, and everything was coded and hooked up to my laptop for testing. Using an oscilloscope, the image on the right, you can see our final waveform. Some of the statistics, our ending frequency was around 60 hertz, which was within the usable dominant range. There is a little bit of noise which still needs to be filtered out, but that will be looked at for future work. And next up, we're going to show you a brief demonstration about how our motor works. All right, everyone, here's our semi-final get-up. There are a few things that we still have to work out, but in general, this is how the motor will work within the hand, or motors, since we're going to have multiple. So essentially, as the voltage increases or as the electrical impulses start coming down towards the hand, i.e. a person will want to use their hand, the motors would start turning essentially. Obviously it's jittering right now, but essentially the motor would start turning, allowing the person to be able to flex their hand, grasp, clasp, pinch something, do whatever they need to do to allow more flexibility and more range to use their prosthetic hand. But as I decrease the voltage, meaning when the person is done using their hand or is starting to ease up, once I hit that threshold voltage, the motor would go back to the starting position and would essentially turn off. Obviously, we're still going to look into completing it and troubleshooting, but that's essentially how the motors will work.
The first piece of code developed to control the servos was done using Arduino's IDE and C++. We did this by using its servo library and pulse width modulation. It takes the EMG input as either a digital high or low if somebody flexes, and if it's high, it'll rotate the motor 90 degrees, and if the signal is low, it'll rotate the motors back to 0 degrees. Since we were having issues with the servos and servo libraries, we decided to create a second set of code that essentially works on the same principle as the first and uses a digital high and a digital low to start and stop the servo motors. In terms of results for this project, we saw success in each of the individual components, though each of them do still have issues that need to be resolved. The mechanical components were able to actuate and move. The electronics were capable of powering the servos and collecting EMG data. The software was able to allow the servos to be moved, but the problem is that we weren't able to bring the components together into one complete cohesive prosthetic. The project was an overall semi-success, but we would like to continue this project to make it a complete success.
As far as the challenges that we faced during the project, there were quite a few of them. Modeling design error, time constraints. Obviously, we still want to continue and finish the project, which we're going to do. Issues with Arduino server library, cost of materials, because we all know electrical components and 3D printing components can cost a lot from time to time. 3D printing, not everything will essentially come out the way you want it to come out all the time. Access to materials, scheduling and COVID safety. We weren't able to really all meet in person together, but we were still able to do a lot, even though we were, even states apart sometimes. And some of the prosthetic not working with us.
In summary, we were able to build a functional hand prototype, but it needs some tweaking. However, at least we were successful in establishing the process of making each of them and designing them at the prototype stage, which was a good learning experience for the future. We will continue to make adjustments to the completed prototype prosthetic hand to achieve our final goal.
For future work in this project, we'd like to integrate a signal rectifier for the EMG and create a program so that the analog input of the signal can be used directly. We'd also like to make more robust code so that we can allow for multiple different grip types of the prosthetic and also have a nuanced understanding of how those EMG signals are interacting with the prosthetic. We'd also like to develop a GUI so that we could test the hand without needing an EMG signal. We're considering using p5.js in order to achieve this. And we'd also like to alter the design so that we can improve the movement in each of the joints in the prosthetic. Thank you for your time, and I hope you enjoyed the presentation.